we're going to consider all three trigonometric functions for the angle that is in the first quadrant. And let's see, if the first quadrant, x-coordinate and y-coordinate, they're all positive, and radius is always a positive no matter where you are, right? So they write all. All three trigonometric values take positive values if the angle is in the first quadrant. Does that make sense? Let's look at the second quadrant. There are three trigonometric values. I want to point out which one is a positive. So here, y divided by r, y is a positive, right? How about x over here? X is negative, so negative divided by r always a positive, so that's negative, right? How about tangent? Y positive, x negative, so altogether negative. The only positive value among these three is a sine up there. Okay? How about down here? Y is down there, so y is negative. X is also negative, right? How about tangent? Negative divided by negative, so it becomes a positive. So tangent is the only trigonometry in the third quadrant that remains positive in here. How about the fourth quadrant? What is a positive here? X-coordinate is positive, right? Y-coordinate negative. So y-coordinate negative, sine is negative because r is negative. And cosine theta, x is positive, so cosine is positive here, right? X-coordinate positive, r is always positive. How about y divided by x? One is positive and the other is not, so it remains negative. Cosine is the only trigonometric value in fourth quadrant that remain positive. Is that right? Yeah. So, well, you can just memorize all these things I say here, but think about the principle. Everything positive in the other three quadrants, only one of the trigonometry of the three is remain positive. Think about coordinates that's involved in here. Y-coordinate, x-coordinate, things like that. Okay? That's a good information. So we're going to go through some exercises that using the special angles and things like that. The main purpose of this exercise is not only do you just write down this definition formula in here, you actually address everything that is involved in the statement of the definition of a trigonometry of all functions of all angles, and you show how this thing plays in the examples. So do not just focus on how to get that answer, focus on to showing all these ingredients that is involved in this definition, right? The book doesn't phrase it that way, but what I want and what I value the following exercise is that you apply everything is in this box to actual example. Okay? That's what you need to show. So I'm going to phrase it like this. Use the circle definition to answer, to compute the following and things like that. And what you have to show me is not just the answer, but draw the circle, draw the angle correctly, not random like this, and identify the size of the circle and coordinates and all that. And then write down sine theta, cosine theta, tangent theta. Actual examples of applying this definition. All right? So let me phrase that here. Use the circle definition. Circle definition to compute, backtracking here, compute, blah, 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 whatever, that, compute the following, compute, that's how the phrase of a question is going to appear in the test. Right? So let me show you. Before we do that, we're going to remind ourselves about the special triangles. We're doing this without using the calculator, right? So special triangles first. There are two types of special triangle, remember? That uses symmetry. Symmetry, nice symmetry. What was the first symmetry that we considered there? 45, 45, thank you. So that's isosceles, right? 45, 45 degrees, and that's 90 degrees. What are the numbers of spread here? Shortest one is always what number? Simplest number? 1. So shortest one is 1, 1, right? Remember the other side? What was that? square root of 2, Pythagorean theorem. That was the first special triangle. Second special triangle I call a tall triangle, taller than this one. That comes from equilateral triangles, right? So that looks something like this, with a bit of exaggeration, 90-degree there. So what are those angles? Equilateral triangle, think about that. What is one of the angles? 60-degree. 60 degrees here. What is the other one? 30-degree, therefore. They're together, they make 90-degree in the right triangle. The shortest length is always 1, and let's think about symmetry and what are the other numbers. What is this one was a 2, right? 2 times the bottom, and what was the remaining one here? Root 3, right? These are trigonometric ratios of right triangle that we looked at it here. Now we're entering the slightly more general situation there. All right? Any question? Find trigonometric functions angles and find cosine of 135 degree. Okay? If you take out your calculator and hit cosine 135, and calculator will compute it. Right? You can compare your answer with that one, but it's not going to be usually exact. So if you have calculator that's fancy enough and that's going to calculate exact value, but it's not the answer, you have to show all the procedures, right? That's what I want to see. All right, let's do that in here. So how do I phrase this problem? Use the circle definition to compute cosine 135 degree. Does that make sense? That's the phrase that I'm using in here. Not just calculating. You have to show how this definition play into this. Let's locate 135 x here. This one you should know. I think you can. Many of you will know. Where is this 135? Second quadrant and third quadrant. Second quadrant, less than 100 degree, 80 degree, greater than 90 degrees. So this is a 0 degree, going 90 degree, 180 degree is in between here. Okay? Well, there are many ways to answer this one. The principle is the following. 135, I think it's right in the middle in here. And you can, erase and sketch it correctly. This is 135, is that right? Just stop it at some point, 135. All right, so that angle here is 135. Is that okay? And that's terminal point. You decide I'm going to stop right there. I don't know how long this one is, just this terminal side. Next thing we do is that we're going to project onto x-axis. Just remember, you project onto x-axis. Can I project onto y-axis? And you can make things work in there, but let's just stick to projecting onto x-axis. Always work. All right? So here's a point that I'm going to project it down to x-axis like this. 90 degree, not like, arbitrary direction. You go 90 degree down to x-axis. That's what we mean by projection. From there we create right triangle, right? Is that right? Okay, that's next thing. Next thing is that you have to draw a circle out of this point here with that radius. Okay? But before we do that, we're looking at here 135. Let's figure out about the angle that is involved in this right triangle I just created. How about this angle right here? How do you calculate that angle? Right, 180 minus 135. Is that right? 180 is all the way to the negative x-axis. You subtract 135, and that's how much is remaining. So what is it? 45 degrees. So that's 45. That makes the other angle also 45. Is that right? So by doing that, we created isosceles right triangle. And 45, we know what's going on with that triangle, right? And then we're going to put the number we want. What are those numbers? 45, 45, we want it to be 1 here, length 1, right? 1 there, right? Square root of 2. That's what we want, right? So that determines the triangle also is going to determine the size of a circle. Doesn't matter which size of a circle you use, the ratio will be the same. Do you have a question, Spencer? Right, so that's why I put this little length mark here. So only the length is 1, but what he was saying is absolutely right. You have to be careful when we identify x coordinate there. So I'm identifying the length is 1, okay? And the next thing is that you actually have to draw the circle. Do your best, draw the circle like this. All right, let's say that was a perfect circle. But how do you make this one perfect circle? Although it doesn't look like a perfect circle, you state something, right? What do you state it? The equation of the circle, right? What is the equation? X squared plus y squared is r squared, right? What is r here? Radius of the circle I just drew. What was the radius of the circle? Before we didn't know, we put it square root 2 there. That's the radius right here. So if you square it, it's going to be like this. So in a simpler form, x squared plus y squared equals 2. That's the equation of this circle, right? And identify carefully that r is actually root 2, not 2, right? This is the equation. R is root 2, not 2. What you see on the right-hand side is not r, it's r squared. Therefore, if you put the square root to that, then that becomes r. Does it look like the pretext of the definition of a trigonometric functions done to this particular example, right? What is theta here that we're looking at? Answer is now 45, right? 135 is the angle we're looking at in here. All right? So let me go back to our definition. We just done this part carefully with actual example. 135. And put some arbitrary size, not arbitrary size, the size we want, so that our information fit into that. Make sense? Let's write down sine of what degree? 135 degree. That thing itself goes in there. Not 45. 135 is, let's see. I forgot to skip the one step. I didn't complete it. I have to identify the coordinate here. I'm sorry that I was rushing. There's no need to rush today. I have to set to myself I'm going to go really slow today since it's class before the test. I'm backtracking. I wasn't complete. I didn't identify this point right there, right? So let's do that. Sorry about that. All right. So this is about this length here, x coordinate and a y coordinate. And like the Spencer told us that this one is going to the left side from the origin, right? So it gets -1. Okay? And then to get to the final point, you rise. So that's a positive 1. It's a positive 1. The coordinate of that point is a -1, comma positive 1. Or you can, hey, that's in the second quadrant. X coordinate should be negative. Y coordinate should be positive. That's another way. The magnitude comes from these two sides of the triangle. Right? Horizontal goes to x coordinate. Vertical side goes to y coordinate. Think about which one gets negative, which one gets positive. Okay? Then we go to sine of 135. What was the definition of sine of theta? Y coordinate of that point, right? But we don't put y there, the actual coordinate. What is it? 1 is the y coordinate of that point. Okay? What is the radius? Be careful here. Root 2, not 2, so square root of 2. So that's the definition applied to actual angle 135. Make sense? Let's do cosine 135. That's the actual question here. Cosine 135 degree is x coordinate, right? What is the x coordinate? -1 divided by square root of 2. All right? And how about tangent? 135. Right, 1 over -1, better known as -1, right? Does that make sense? All right, so that's probably one of the problems you're going to see in the test, or mock test, right? Okay, let's practice. Any question? All right, these are the examples. why don't we try something different? I think this number 12 looks good, and also secant 300 looks good as well. So we're going to do these two problems. All right. Again, it is also saying the exact values, and that's how I'm going to phrase it. If it is related to, you know what, related to exact angles, exact values, special triangles. Okay? Here we go. So I forgot to announce it here. These two problems are exercises. Here. Alright, if for the problem 12, if you project onto x-axis, you still get 45 degree. Agree on that part? Yeah. So if you look at the both sides, it's 1, 1, but this time, starting from the origin, you go to the left, so it's negative coordinates, you go down to get to that terminal side, and negative. So coordinates are -1, comma -1. And the radius never changes sign. It doesn't become negative root 2 because it's going down or anything. It's always a positive root 2. Alright? So this time the tangent is only positive value, and the other two, sine and cosine, is negative value. Just like that sine SIGN thing that we looked at for each of the quadrants. Tangent is the only value, the positive. Is that right? Any question about number 12 before we begin number 16? Yes, Matthew. It depends on, if this were in the second quadrant, you actually subtract from 180 degree. If you're in the third quadrant, then it exceeds 180 degree. So you subtract 180 degree from the other angle. If it is in the fourth quadrant, which is the number 16, then you think about what to subtract from. But if you sketch it, at least if you locate it correctly, then you can think about how to get that angle that of the right triangle you look at. So first thing you have to do is that you should do this one from the terminal point. Go on to x-axis, which is different direction for each of the quadrant. And then you can think about, so each of the quadrant is different rule. Sometimes you subtract from 180 degree, sometimes you subtract 180 degree from something else, right? Question about this one? And I got this 300 goes all the way to the fourth quadrant. And if you project it onto x-axis, you wanted to know the remaining angle in here, and that's 360 minus that 300 you subtract roughly the 60 degree. Once you figure that out, rest of the part is the same. So that's the part that is slightly different. Which one to subtract from where? So we got 60 degree. Is that right? Okay. So from the same group, this angle is just given in radian. One way is that you convert it to degree, and then you repeat exactly the same thing. At least convert to degree and locate where the angle is, first quadrant and second quadrant and fourth quadrant. And from there, subtracting 100 degree is subtracting pi, things like that, right? So it's the same procedure. But without converting, if you remember the following, and then it's easy to locate which quadrant they are. X coordinate is here, y coordinate is there, right? It's an angle, and this angle in here, theta, is 0 radian, correct? And this is where the first and the second quadrant is divided. So what is the angle here at the, it's a pi over 2, remember that part? Pi over 2 radian. So if you remember at least this part, you can easily kind of compare it here to figure out which quadrant it is. How about all the way over here, angle this side? Theta is pi radian, right? 180 pi radian. And if you go all the way here, that's going to be 2 pi. But what about this one down here? What is the angle? If the terminal side is pointing downwards like that? Right, 3 pi over 2. Or you can calculate pi over 2, another copy of pi over 2, that's pi. Another copy of pi over 2, that's 3 pi over 2. Another copy of pi over 2, that's 2 pi. All right? So if you have these borderline angles kind of understood, then you can compare that. For example, number 23. Right. Pi is there, right? So think about 2 over 3. Is 2 over 3 this, except the pi, it is 1/2, right? So I think 2 over 3 is greater than 1/2. Is that right? Yeah. So it's somewhere here. It's definitely less than 1. Less than 1, since that's what's in front of pi. 3 over 2 is less than pi. I mean less than 1. So it's before pi and after 1/2 pi. So you know it's located somewhere here. That's one suggestion. But you can always convert it to degree and get the quadrant correct. Is that okay? All right. So let's look at number 23. And I'll do the first bit. And I want you to finish the rest of the bit. So here is an exercise. I'm going to do just the first bit for you. So here's the angle, x-axis, xy plane angle. So again, 2 pi over 3 is in the second quadrant, right? So I'm going to locate it here. That's 2 pi over 3. And project it onto where? X-axis. So you go down to x-axis like this and figure out this angle there. And how did we do that? We're subtracting something from something. So what are we subtracting from? I think you go all the way to pi minus that angle. That'll give you this much of angle, right? So pi minus 2 pi over 3. Is that right? So that's that angle. Of course, it's 1/3 left and the pi over 3. Is the arithmetic okay? Yeah. Right. So that pi is entire angle going around like this. And if you want just that angle, because you want to figure out what kind of triangle we're looking at, we want this angle, right? So this entire 1/2 rotation minus whatever is given in here, which is 2 pi over 3. You subtract off that. So that's pi over 3. So that's pi over 3. And what about the other one? Anybody remember pi over 3 in degree? I think it's 60 degree. 60 degree, yeah, 60 degree. It doesn't say radian, we assume it's radian, 60 degree, and that's 30 degree. 30 degree is a half of 60 degree, so it's, what is half of pi over 3? Pi over 6, yeah. But we want to know this as a 60 and the 30 triangle. This is not quite to the scale, right? Because it's supposed to be, if it's a 60 and that's 30, it's supposed to be a tall triangle, right? Maybe you can correct it, not knowing you're just doing this calculation, right? You have eraser and then correct it. So, but if it is not in the quite correct scale, but let's see if you can spread the number correctly. 60, 30 degree triangle, correct? So, you see that if it is a real 60, I have to correct it, and everybody's just misled by this one. Here, that looks more like 60 degree, right? That's the angle there, and that's the angle. So, bottom is the shortest one. What is that? One length is 1, and height here, √3, and radius is 2. And then here's the terminal point, and you draw a circle around it like this. So let me pull that out here. That terminal point, who wants to go for the coordinates? X coordinate? -1? -1. Y coordinate? Sort of positive √3. How about the radius involved in here? 2, that's hypotenuse of the triangle. So with that, we can calculate sine of what angle are we calculating here? 2 pi over 3. The starting from initial side all the way. That's 2 pi over 3. This angle we're doing. So what is it? Sine of 2 pi over 3 is positive √3 divided by radius 2, right? That's the answer. Let me finish. Why not completing all that? Cosine of 2 pi over 3 is -1 divided by 2. Tangent 2 pi over 3 is positive √3 divided by negative 1. So it's negative root 3. Those are the three trigonometric values for the angle 2 pi over 3. Okay? All right. Apparently that if it's doing things in terms of pi that's more uncomfortable than doing the degree, then do things in the degree, and at the end make sure you put answers in this mode, because that's what they wanted to write. That'll be fine. Any other question? Purpose of going through this example is make you feel a little bit more about all the details that is involved in the definition of the trigonometric functions of all angles. So I'm going to draw this circle many, many more times throughout the sessions. Once I believe you're all now really internalize this one, get used to it, I'm going to stop drawing the circle. But at some point, I'm going to hit the barrier that, can we stop drawing those circles? Everybody will say that, and okay, I think everybody gets it now. But I'm going to draw this a lot of circles. And again, the purpose of that is that you understand the definition. That's the most important part in this at this stage. God, help me out here. Spelling of this word is always challenging. Pythagorean identities. All right. These identities shows up everywhere, all the way. Let me say this again, all the way to the end of the higher mathematical curriculum. They use this a lot. It's just interesting thing. That. All right. So first identity is the following: that sine theta. You know what we mean by sine theta now, right? Theta is not just a small angle. It could be 7,000 degrees and negative 7,000 degrees angles. Those are sine theta. Go around, end up somewhere on the edge of the circle. That's what we mean by sine theta, right? And if you square that, and cosine theta, and you square that, we don't know what theta is. Anything. What happened is that they magically cancel each other and just becoming constant, whatever theta is. So they don't call this one equation, right? They call this one identity. That means it is not satisfied for some values of theta. All values of theta, it is satisfied. For example, x plus 1 squared equals x squared plus 2x plus 1. If you don't know what's happening in here, you might look at this as an equation. But if you know what's happening in here, there's more than an equation. For what kind of x value is left-hand side is equal to the right-hand side? Sounds like an equation, but the answer is no matter what your x is going to be always equal to the right-hand side. The solution of this equation is all real numbers. That special equation is called identity. No matter what your x is, it can always equal to each other. Right? If you actually multiply x plus 1 to itself, expand out, and you will get this one algebraically. All right? So you learn this algebra. So you do that. But there's no algebraic way of going here to there. That's a slight different flavor. But it is still identity. No matter what theta you stick it in there, if you use a calculator, try sine 72 degrees squared plus cosine 72 degrees squared. Hit enter, it's going to be 1. Cosine 47 degree, cosine 47 degrees squared is always 1. Right? That's the identity. Another identity is that these two things shows up a lot. 1 plus tangent theta whole quantity squared equals secant theta whole quantity squared. If you do a little bit of algebra, you can go from the first equation to the second equation. But the second equation is based on the first one. First one is a fundamental one. It is called Pythagorean identities. Okay? Sine squared plus cosine squared is 1. And remember, those angles for both terms must be the same. If it is cosine 45 squared plus sine 75 squared is not 1. The angle has to be the same. Okay? So let's have a little break on this one. So I'm going to show you why this one is true. Of course, trying 2 million different angles doesn't establish this fact, right? We will never establish this fact by trying actual angles and using the calculator. Remember, calculators and approximate values? So you don't really prove this one is exactly 1. Okay? So going back to the circle, and there's an answer there. So here is a proof of the first statement. It's also help you to think about this circle definition once again. So I'm going to put that. This is not the specific angle we're talking about here, some arbitrary angle. So I'm going to put that in the third quadrant this time and going kind of backward, no matter what the theta is. All right? And what is the x coordinate here? X there and y coordinate. And what is the equation? Remember the equation? X squared plus y squared equals r squared, right? That's pretty much it before you write down in sine and cosine. And what is the sine of theta? Y divided by x. Cosine theta, sorry about this, y divided by r. Cosine x divided by r, right? I just stop it here because the statement only concerned sine theta and cosine theta. That's why I just stated 2 of them. Okay? So this is just a repeat of the definition. Now, what this identity is claiming is the left-hand side is going to be simply 1. So I'm going to do that left-hand side. Okay? What is left-hand side? Sine theta squared plus cosine theta squared, right? So it's a sine theta squared plus cosine theta squared. I'm not setting this on equal to 1. I have to explain why this one is 1. But what do we know about sine theta in terms of coordinates here? That's y divided by r. Is that right? That's what sine theta is. And you square it. What is cosine theta? X divided by r. And you square that, right? That's left-hand side. We continue. We have to keep calculating. It happened to have common denominator. Do you remember this square distributes over division and multiplication, but not for addition, over addition. So here's x squared divided by r squared. Does that make sense? You have a common denominator. You can put it into a common denominator like that, right? And what's the numerator? Y squared plus x squared. Who remembers about y squared plus x squared? That's r squared. Any x coordinate, y coordinate on the circle satisfy this circle equation. X squared plus y squared is going to be always r squared. So that's r squared in the numerator. Denominator is r squared. So all those things unknown on arbitrary stuff becomes just simply 1. And I show the left-hand side is indeed just 1 all the time, no matter what your theta is. That is called Pythagorean identity. All right? We will never go through this again every time. It's just instructors in the calculus courses and expect that you know this thing. Sine squared plus cosine squared equals 1. All right, they got lazy. Use the following notation. Instead of doing this multiple parentheses, they begin to use notation like this. Sine and put the superscript here and put the theta out there. So the meaning of this one is this whole sine theta quantity is squared. But you will see this a lot, right, in the book. And cosine theta whole quantity squared is now abbreviated like this, cosine squared there, theta, and that's 1. That's the notation they use. Is that right? All right. So you believe this is always true? Yeah, that's the explanation. This is a theoretical problem. If somebody asks if this is going to on the test, my answer is always yes. Remember that part that I explained to you? But I give you the answer today that it's not. This is not going to be on the test. But this is an example of a theory problem which will be on the test, session test 2 and test 3 and test 4, but not in the test 1. Okay? And you know which one is going to be on the test, so you can prepare your answer perfectly like this. All right? So that's theory. One more problem and that's it. All right, I'm going to save this one. Continue. Calculus 006. It's February already. Point 1. Right, last one is also a very good good one here. So let's watch out. Example is the following. Tangent theta is 2/3, and theta is in the third quadrant 3. Find the cosine theta. Okay? Also, I'm going to phrase it like this. Use the definition. Remember that clause? Use the definition of a trigonometric functions of all angles to compute cosine theta. Right? Don't just memorize the procedure to get to the answer. I need to see the circle once again. That's the idea. All right. So here's a solution when I see it. Go ahead and draw the circle. XY, and here's a circle. We don't know the size of it, but we know the equation must be in this shape, x squared plus y squared equals r squared, right? Okay? And angle is in where? Quadrant 3. So we don't know exactly where it is. I'm just going to put some arbitrary position in the third quadrant. And that's the angle right here. So it doesn't matter which way you rotate. And if you end up at it here, that coordinate, coterminal angle has the same coordinates, right? So I'm just going to pretend it's a simple angle like this. Why not? Theta. Is that right? And x comma y is there. So that's the whole definition thing is written down all over again. What we know is that tangent theta is equal to 2/3, right? So how does this tangent theta look like in the definition? Supposed to be y divided by x, right? So one method is that y is going to be 2, x is going to be 3, and we're done, right? But unfortunately, x comma y is down there where? In the third quadrant, right? So conclusion from here is that y is not positive 2. What is it? Negative 2. And x is negative 3. So that if the negative cancels, in simpler form, we obtain the 2/3 back. Does that make sense? Yeah. So again, you set it to whatever the usual definition, y over x, and think about which coordinate is supposed to be positive, which coordinate negative, and then you can make sense out of it, which is this arrow part. Any question? This is the part that is not true. Yes. Right. So this is a given information, and I wrote down y over x. That's the definition of tangent theta, right? And you match numerator and denominator. So the answer is not y equals 2, x equals 3. You have to go back this quadrant 3 information and figure out which coordinate gets negative and which coordinate gets positive. If it is in the third quadrant, both x and y coordinates are negative, right? Therefore, y must be negative 2, x must be negative 3, and together y over x in simplified form is 2/3 because negative cancels. Make sense? All right. So once you have that, we have x coordinate there and y coordinate there. What we don't have is radius, right? So how do you figure out the radius? You plug it into this circle equation. What is x coordinate here? Negative 3 squared, right? What is y coordinate? Negative 2 squared equals r squared, right? Not r. So what is the left-hand side? Is it 9 plus 4? Is that 13? So 13 equals r squared. So what is r? Positive root 13. Radius is always positive. Now we have x coordinate, y coordinate, and the radius of the circle. Then you can write down the other two trigonometry. So let's see. Cosine, right? So cosine of that angle we don't know. But certainly if you sketch this radius 13 and go to that exact coordinate 2/3, use a protractor, you can measure that angle. We can have an idea what that angle is. No matter what that is. To calculate the cosine theta, all we need is the coordinates and radius. So what is it? X coordinate, which is negative 3 divided by radius root 13. Right? Well, it didn't ask for sine, so let's do that sine as well. Sine theta is negative 2, y coordinate there, divided by root 13. That is the sine and cosine value. Right? So they usually give you one trigonometric value